Okay, let's unpack this. Today, we are doing a deep dive into the absolute workhorses of process control.
Rotary control valves.
Exactly. If you work in a chemical plant, a petrochemical facility, or a pulp and paper mill, these are the mechanical muscle.
They're the power-operated devices that are actually changing the flow of fluid in a system. They're how you control everything. Pressure, temperature, level.
And our mission for this deep dive is to cut through the huge catalog of designs out there.
We're going to zero in on the four main types, explore the really critical safety hazards they present, and then look at how modern smart tech is changing the game for maintenance.
So let's assume everyone listening knows a control valve is a valve body plus an actuator.
Right.
Let's jump right to the big distinction. Linear motion versus rotary. What's the immediate advantage of rotary?
It's all about flow capacity. I mean, sliding stem valves, like a globe valve, they have a pretty convoluted path for the fluid.
It's restricted.
It is. But rotary valves, they operate with a rotating shaft, usually just a quarter turn. And when it's fully open, you get this virtually unobstructed straight-through path.
Which means much higher flow for the same size valve.
That's the core reason. It's a huge mechanical advantage.
Okay, that high flow capacity is a perfect place to start. Let's talk about ball valves. They seem like the classic example of straight-through flow.
They are. A conventional ball valve is, it's essentially a sphere with a hole drilled right through it, sitting between two seals.
And that 90-degree rotation is fast, simple.
Super simple, minimal resistance to the fluid.
A valve that feels like it's built for just on-off service, like a light switch.
That's its strong suit, for sure. But when you do use it for modulation, for throttling, its flow characteristics actually mimic the equal percentage curve you see in globe valves.
Which is valuable.
Very valuable. It means you get fine control when the valve is nearly closed, and then the flow ramps up dramatically as you open it wide. It gives you a massive control range.
Okay, but here's where we get an interesting twist in the design. The characterized ball valve.
Ah, yes. The segmented or V-port ball.
It moves away from that simple sphere. It's got that V shape. Why? Is that just for a better flow profile?
It was engineered to solve one of the toughest problems out there. Throttling slurries and fibers.
Things that clog.
Exactly, that V-shape, that contoured edge. It's not just about flow, it's a self-cleaning feature. As the valve closes, that edge literally slices through any solids.
So it can handle things like paper stock.
Paper stock, mining ore, you name it. It prevents clogging and ensures a tight seal.
That is a perfect example of design being driven by a very specific application.
Yeah.
Now, what about the trade-offs? They're tough, right? High pressure, high temp.
Oh, yeah. They can handle up to, 2,250 PAA and over 300 degrees Celsius with the right metal seals.
But you'd never see one in, say, a pharmaceutical plant.
Absolutely not. It's all about contamination.
Why is that?
The design itself. It creates these small body cavities, behind the ball and around the stem. Fluid gets trapped in there.
It becomes stagnant.
Then that can foster microbial growth or other contamination. In an ultra-clean process, that is an unacceptable risk.
Okay, so if the ball valve's weakness is trapping fluid, that's a good pivot to our second type, the rotary plug valve, where sealing is really the main event.
That's a great way to put it. Also a quarter-turn valve, but it uses a plug, not a sphere. And there are three main ways they handle the seal.
What's the first one?
The lubricated rotary plug. And it's exactly what it sounds like. It uses a special lubricant that's pumped in to reduce friction and, act as the seal itself.
And I'm guessing the big downside there is maintenance.
A significant maintenance burden. You have to top up that lubricant sometimes after just a handful of operations, or even just one cycle depending on the fluid.
So you need constant attention.
You do. Now compare that to the second type, the sleeved rotary plug valve.
Which is non-lubricated.
Right. It completely eliminates that headache. It uses a soft insert, usually a PTFE sleeve, that sits between the plug and the body. That's your primary seal. Much lower maintenance.
And that brings us to the most mechanically interesting one, I think. The eccentric rotary plug valve. What does eccentric mean here?
It means the plug's seating surface is offset from the center of the shaft. So when the plug rotates, it swings into the seat to seal, and then it swings out of the seat when it opens.
So they don't scrape against each other.
Exactly. No scraping, which dramatically reduces wear.
And because it's non-scraping, I'm guessing it also has that self-cleaning advantage we saw with the characterized ball valve.
Absolutely. That eccentric action makes it inherently self-cleaning. That's why you see it in really erosive services, like in mining or coking units and refineries. It's robust.
But there's a trade-off. It's great for slurries,
Yeah.
but it has a much more limited control range.
It does, about a third of an equally sized ball or globe valve.
So why is that limited precision okay in some plants?
Because it's a champion in constant process load applications.
Hmm.
If your process just runs steady hour after hour and you need a tough valve that can handle grit without wearing out,
That limited range doesn't really matter.
it doesn't. You set the flow and you leave it. It's about stability over surgical precision.
Okay, let's shift focus to the big picture now, literally.
Mm-hmm.
The workhorse of large piping systems, the butterfly valve.
Right. Butterfly valves are simple, they're economical, and they really shine once you get to those large line sizes. 200 millimeters, 8 inches, and up.
And the construction is simple. A disc on a shaft.
Just a disc on a shaft in the middle of the flow path. And a key characteristic is that they are a high recovery valve.
So if you're a listener trying to save on energy, why does high recovery matter?
Because it hits your pumping costs directly. High recovery just means the valve has a low pressure drop when it's open. The fluid recovers most of its pressure on the other side.
Less energy needed from the pump.
That's a huge operational saving over the valve's life.
Now, they're economical, but the standard butterfly disc has issues with throttling. It's limited to about 60% rotation, right?
That's the classic problem. Beyond 60 degrees, the disc gets really unstable. The torque needed to move, it just jumps and control gets sloppy.
But there are workarounds.
There are specialized designs like the fishtail low torque disc. It manages that turbulence much better, so it can actually get a full 90-degree opening while staying stable enough for throttling.
And what about sealing? They aren't famous for being bubble tight.
No, not on their own. They usually need some help. You can add elastomer liners bonded right to the body to get them to meet really tight shutoff specs like ASME Class 6.
But they still have the same contamination problem as ball valves.
They do. Fluid can get trapped around the disc and the stem, so not for high purity systems.
Okay, we've covered high flow, slurry, large lines. Let's just briefly touch on the real niche player, the position disc valve.
These are a whole different animal. No traditional plug or disc. It's 2 discs, one moves, one is stationary, and they both have holes in them.
And you get control by covering and uncovering the holes. You got it. And these things are engineered for one thing, survival under extreme pressure.
Up to 10,000 psig. To do that, the discs have to be made from incredibly hard materials like tungsten or carbide, polished to a mirror finish. It's a very high-performance, specialized solution.
So now that we've covered the 4 main types, let's talk about the supporting components, like the bonnet.
Right, the bonnet. It's the part that houses the packing assembly, which is what creates the seal around the valve stem so fluid doesn't leak out.
And most rotary valves use an integral bonnet.
They do. It means the bonnet is just machined right into the valve body casting itself. It simplifies the design, reduces cost.
But what about extreme temperatures? That packing must need protection.
Absolutely. For extreme heat or cold, you use an extension bonnet. It just physically moves the packing farther away from the process fluid.
And for cryogenics.
For something like liquid nitrogen down to minus 252 Celsius, you need a specialized welded cryogenic extension. It creates this long insulation zone where gas forms and protects the packing from that profound cold.
Let's talk about how you install these, because that dictates everything about servicing them.
Definitely. You've got welded ends, which are great for preventing leaks, but they are a nightmare to remove.
And threaded ends.
Economical for small valves, but forget about servicing the internals. You just can't get inside.
Which makes the wafer style kind of the maintenance hero here.
It really is. The valve body is just sandwiched between 2 pipe flanges. You unbolt the flanges, the valve slides right out. Easy removal, easy replacement, minimal downtime.
And for those expensive alloy bodies, there's a clever cost-saving design. The Van Stone style.
That's the smart money move. The valve body might be a pricey alloy for corrosion resistance, but the big, heavy flanges holding it in can be made of cheaper carbon steel. It's a great system.
Let's pivot now to safety. This is non-negotiable. No matter the size of the valve, you have to isolate multiple energy sources.
And this is where rigid adherence to protocol is mandatory. You have to isolate and vent 3 major energy sources. First, the high-pressure process fluid itself.
Which can be thousands of CI.
Thousands. Second, high-pressure instrument air for the actuator, which can be up to 100 psi or so.
And the third one, the most dangerous one, is the stored spring energy in the actuator.
That is the single most critical danger point when you separate an actuator from a valve. Those springs are under tremendous force. They're designed to slam the valve shut or open in an emergency.
And if you don't relieve that energy correctly,
Catastrophic release. It can lead to serious injury or death. There is just zero margin for error.
plus you still have the chemical hazard from the fluid that was in the pipe.
That's right. Before anyone touches that valve, you have to know exactly what was in it and decontaminate it properly. That could be a simple water wash or something much more involved, like an acid bath.
Lockout, tag out on everything.
Every single energy source, pneumatic, fluid, electrical, has to be locked out before a single tool touches that assembly.
Okay, we've covered designs and dangers. Let's finish with how technology is changing maintenance, moving it from reactive to proactive. The smart valve.
This is all driven by modern smart valve positioners, or DVCs. These things are constantly monitoring the health of the valve and actuator while it's running in line.
So you find problems before a failure.
Long before. It prevents those costly, unexpected shutdowns.
And it gives you a really simple indicator, right?
Super simple. Green means everything is healthy. Yellow means a subtle fault has been detected, so you should schedule maintenance for the next planned outage.
And red.
Red means a serious fault is actively hurting control right now and it needs immediate attention.
Can you give us a specific example, a diagnostic that might trigger a yellow or red alert?
Sure. A great one is air mass flow diagnostics. It's constantly measuring how much air the actuator is consuming just to hold its position.
Okay.
If that steady state consumption jumps over, say, 14 standard cubic feet per hour, that's a huge red flag. It points directly to a mechanical problem, leaky piston seals, a damaged diaphragm, a bad relay, the valve is bleeding air, and it needs to be investigated.
So if a diagnostic does lead to a full overhaul, what's the critical data a technician needs on that job card?
Oh, that card has to be perfect. It needs the plan ID, the tag number, serial number, body size, the actuator requirements, the operating range, every detail.
Because a tiny mistake can have big consequences.
Huge. If you're removing packing, for example, you have to use a special tool, like a formed wire hook, so you don't scratch the stem shaft. Even one tiny scratch will compromise the seal and the valve will leak as soon as it's back in service.
That's a great summary. We've covered the big differences between ball, plug, butterfly, and position disc valves, the critical safety rules, and the power of smart diagnostics.
So as a final thought, let's connect the two extremes we talked about. On one hand, you have those massive economical butterfly valves available up to, 96 inches?
Right, for high flow where cost is a huge factor.
And on the other end, you have the position disc valve rated for 10,000 psig and needing these exotic carbide discs to survive.
The ultimate containment challenge.
It is. So think about the engineering problem here. How does the need for precise control at that insane pressure, which demands these hard, rigid, specialized materials, inherently limit how big or complex you can make that valve?
Compared to the simple, huge butterfly disc.
Exactly. And what are the hidden costs of that extreme performance? It's not just the price tag. It's the specialized handling for those materials, the complexity of inspection, the skill level needed for maintenance. It shows you that choosing a valve isn't just about flow rate. It's about calculating the true total cost of performance over its entire life.